Delong Discussions. My name is Daniela Vieira. I'm the application engineer at Delong America, and today we will be talking about low voltage electron microscopy for biological thin sections. Here's a little bit of our agenda: introduction, the current challenge, introduction to low voltage electron microscopy, LVEM 25E for biothin sections, some applications, conclusions, and by the end, we are gonna run a live demonstration here in our 25E. So, introduction. TEM provides an understanding of the structure and organization of the components of tissue, cells, and organisms. It provides diagnostic criteria, and current high voltage TEM is the standard methodology for ultrastructure evaluation. If we see here, we have a draw of a cell with a few structures that we would like to see it in TEM, so like mitochondria, nucleus, and that's what TEM will provide. So in here, we have a picture of mitochondria. As we can see, it's a very detailed image of the structure, high resolution when compared to light microscopy. And for about 50 years, TEM has advanced the understanding of cellular ultrastructure among biologists and pathologists. High voltage TEM, it's a nice technology. However, it has its own limitation, and we will be discussing it in a few seconds. Just before, I want to know from you, what are the biggest challenges you face when image biological samples? So we have option A, sample preparation. We have B, being damaged. And we also have C, accessibility, complexity of high voltage TEM systems. Please feel free to answer. And we are gonna end the poll in about 30 seconds. All right, as we can see, we have sample preparation and accessibility of high voltage TEM systems. And that's true, and we will be discussing it in a few seconds. Let me just close the pool, right. So indeed, complexity of sample preparation, how to achieve the best image contrast, sample damage, and complexity of high voltage TEM systems are the fundamental challenges in bioelectron microscopy. If we talk about sample preparation, it's an extensive process: fixation, dehydration, embedding, and for high voltage TEM system, stain is mandatory to allow you to have a contrast in your image. And so it's usually done with uranyl acetate and lead citrate. However, uranyl acetate is radioactive and also carcinogenic, and lead citrate is carcinogenic. Another challenge for high voltage TEM system is the destructive beam energy. I will just show like a few examples here. If we see the first video, this is a gold bead. It's a inorganic material, and at higher magnification and higher accelerating voltage. And as we can see, when the beam reaches the bead, it moves. So you see the structural planes, they are moving, and you see that movement. So imagine what it can do when we are talking about a biological sample, organic sample. And in the second video, I have here a bacteria that has been imaged in high voltage TEM. And what we see is like the damage of the material because of the high energy. The high energy breaks the covalent bonds in the molecule of the cell. So by the end, you lose your information, you lose your shape, you lose morphology, and all the structures that you want to analyze. And in the last picture, I have different pictures of proteins. So when I increase the electron dose, I increase the beam damage, and I also lose a few information from the sample. And high voltage TEM systems also require high investments, specific and large facility, complex installation, operation, and maintenance. and qualified staff. Here in our picture, we can see a standard high voltage TM system. So two things that I want you guys to observe here is an entire room for the equipment. Then we have the cooling system behind the microscope, what's mandatory for high voltage TM system, and also the anti-vibration platform. So it's a complex installation and a complex room to have your high voltage TM system. All right, so how can we overcome this challenge while still providing the same advantage? That's why we are going to introduce low voltage electron microscopy. So in low voltage electron microscopy, we decrease the accelerating voltage. And by decreasing the accelerating voltage, we increase image contrast of low atomic number materials. And we can also use permanent magnetic lens instead of electromagnetic lens. This will allow us to have to decrease the microscope size and also the complexity of the equipment. And here it's our 25E. It's all in one electron microscopy. As we can see, it's really compact. We have TM, STM, SEM, and ETS modes available in this unit. And most common applications are biological infections, virus, and in-lab electron microscopy. Again, another here, one example, like the microscope is installed in the lab, so it creates an efficient workflow, is designed to be perfect for smaller spaces, and no special facilities needed. So there is no special power outlet, anti-vibration platform, or any cooling system behind the microscope. And it's all in a single device. So in here, I have an example of interaction of macrophages and gold nanoparticles. My first picture is a TM. The second one is a STM. In the third one, left bottom, we have the SEM, where we can highlight the inorganic particles in this sample. And by the end, I have the ETS, where I can analyze the chemical composition of the sample, showing that I have gold nanoparticles. So LVEM 25E for biofilm sections. Another clue here for you. One of the biggest challenges is the staining. And here I want to know what type of staining procedure do you typically use for sample preparation? We have a standard 2% uranil plus lead. We have different percentages of uranil. It could be less than 2% or sometimes more than 2%. And we have uranil-free alternatives. Please take your moment to answer it, and we will be closing 30 seconds. All right. So as we can see, standard 2% uranil plus lead is, as it says, standard for high voltage TM. And we will be discussing this in the next slide, because this is the main advantage of low voltage electron microscopy. So it allows simple sample preparation. No pulse staining may be eliminated. No real need for heavy metal staining. Uranil is not mandatory. Uranil-free based stains may provide similar or better contrast if you need it in your sample. So it's less toxic and no radioactive. And here I have an example showing the higher contrast compared to high voltage TM. So in the first picture, left and top, we have 200 kV without any staining. And if you see just the picture below it, it's at 25 kV without no staining. So the high contrast is clear in this example, and it's due to increased electron scattering. So we see lower threshold for detecting density difference and fewer artifacts compared to conventional staining. So LVEM reduced the beam damage. By lowering the accelerating voltage, we can reduce the energy of the electrons, and it can minimize the amount of energy transferred to your sample, thus reducing the beam damage. And another advantage is like you can stay longer time imaging your samples, there's no need to run like the samples very quick to not damage them. And again, another example here, the microscope is in the lab. It's one-day installation, very user-friendly. There's no need for a dedicated staff, and it can be placed in the lab, facilitating the flow of analysis. A few applications. So we have here Uranulase low voltage transmission electron microscopy, a powerful tool for ultrastructural studying of cyanobacteria cells that was published in Microorganism. And in their conclusion, they showed that indeed staining is not needed for when you are working at low voltage, low accelerated voltage, and you can replace or eliminate the use of uranyl acetate. And a few examples for ultracellular analysis. So we have cilia, mouse liver, stained sections in here. And the last one is muscle unstained section. So we see the contrast even in the stained sample. Another publication, Journal of Histochemistry and Cytochemistry. This work was the diagnostic electron microscopy of viruses with low voltage electron microscopies. And again, another conclusion is like, indeed, you don't need UA. You can have your final image as good as high voltage TM without the use of staining. More examples, some virus. So I have coronavirus, Portugal virus, and Acanthomweb virus in here. And just one more example is from USCAP. This is the clinical validation of low voltage compact transmission electron microscopy for ultrastructural evaluation of kidney and heart biopsies. And in this work, they concluded that low voltage electron microscope indeed can replace high voltage TM system for renal and cardiac biopsy specimens. And a few like image showing like kidney sections where we have different points of interest, so podocytes, some details of the pedicles, and the last one, the fingerprint structure. So our conclusion before we run our demo. So some benefits of low voltage TM, as we said, the main reason for low voltage electron microscopy is the increased image contrast for low atomic number materials. So it allows for permanent magnetic lens instead of electromagnetic lens, and that's why we can have a compact and a less complex system. It's a direct replacement for traditional high voltage electron microscopes. It's an easy installation, compact, can be installed in a small space, and low facility requirements. There is no need to have a anti-vibration platform or cooling system. And our model LVEM 25E, it has TM, SEM, STM, ED, and ETS modes. A few proud users, we have units all around the world.